It's truly a great pleasure for me to introduce Salvatore Di Girolamo from NVIDIA. So he's a senior software architect at NVIDIA. And before that, he was a PhD student at ETH Zurich. Okay, so Salvatore, please go ahead.
Good. So thanks, Daniele, for the introduction, and thanks for inviting me here. So the idea of today is to go a bit more in detail in some component of the architecture Gil was showing you before, in particular the BlueField-3 DPU and SmartNIC. What I'm saying here applies to both BlueField-3 and also the ConnectX cards. There are some differences, but like kind of concepts I'll go through, they can be applied to both of them. So I want to kind of go through, like introduce it a bit in terms of architecture, what do we offer there, how you can exploit the programmable accelerators that are on this kind of device, and what are the use cases. Actually, it will be just one use case for matter of time, but it will be a juicy one that exploit both in-network features, right, and also like on-device features. So these programmable accelerators, in order to accelerate collective operations, once Gil was mentioning, in the context of AI training, right? So good. So let me start by saying that if we look at today's applications that are deployed in HP systems or large-scale data centers, they vary from cybersecurity, SDN, software-defined networking, storage, HPC AI, which basically today is kind of the most important one, to infrastructure management and so on. What do they have in common, though? I'll say that they have two things in common. One is the need for speed, right? So, and need for speed is not just because you want to execute them faster, and of course it has benefits, right? Because you consume less power, you consume less money when running on this system if your application just completes faster, but it's also because of a need of keeping the system balanced, right? As we increase the power of these GPUs or accelerators, okay, you need to feed them data, right? So this is the need for speed from the networking perspective, right? Because if you don't feed them data, you have a powerful GPU that is just sitting there waiting for data and doing nothing, right? So this is not ideal. So you need to provide data at the same rate the GPU is able to consume in order to efficiently use the system, right? And the second one is, and actually in terms of speed, we are there, right? So you can see, especially if we focus on the last year, so this is the link bandwidth over the years, you can see that basically every 2 years, we are doubling the network bandwidth, right? So we catch up. And another requirements of those applications is the need for flexibility. So this is both related to speed in some sense, because as you want to be efficient, it's not enough just to rely on some heavy software stack that you cannot really manage, and maybe it's given to you and you have no idea, right? Or some well-defined protocol. Now you need to break these abstractions sometimes. You need to go inside and actually customize those infrastructure themselves or protocols, right? So they need some programmability, either in the network or inside the network cards, right? And this is what BlueField offers. So it offers high speed. So today we have 400 gigabits per second NICs plus programmability. So we have multiple accelerators on this smart NIC that the application itself is not the system administrator or somebody else for you. It's you that you can go and specify, okay, this is what I want to execute on the smart NIC, right? And how we get there, what you can execute, we will see. So what I want to talk about then in this presentation is introduction to BlueField-3, a deep dive in one of the accelerators that are on this SmartNIC, which is called DataFAT Accelerator. And finally, I'll go through a use case that has been recently accepted at supercomputing, so it will appear for presentation there. Good. So just quick introduction. We said that programmability and need for speed are the main important characteristics. So we have 400G networking with RDMA and RoCE, so also Ethernet works, and precision timing. On the programmability aspects, we have 16, 64 bits A78 ARM cores, right? So this is basically, you can see this as an endpoint on the NIC. So you have a small CPU on the NIC where you can run your own stuff, right? And a DPA that is more, let's say, a bit more exotic as an architecture, but can give you, let's say, even more performance when used in the right way. Zero trust security, so it offers crypto accelerators that are hardware engines that you can use on the device directly to do crypto, and storage solutions like NVMe over Fabric. If we compare this to the previous generation, so to BlueField-2 is double the bandwidth, 4 times the compute power, and other improvements in terms of zero trust security and storage. Good. So now let's deep dive a bit into the architecture of the BlueField-3. So we have the PCI switch and the DMC. Then we have the first accelerator, which is the ARM subsystem, right? So there you have all these ARM cores. This runs a Linux-based operating system. You can SSH into it and run your stuff, right? Then we have a data path accelerator. So this is RISC-V based and doesn't run Linux. So it's a real-time operating system. It's an event-based architecture, as we will see. And then a programmable pipeline. This is really deep into the internals of the NIC. So you can really say, okay, for each packet, I want to inspect something, I want to change something. So if you are competent with P4, is in that direction. And then we have the hardware accelerators. So these are not programmable, are kind of black boxes that you just say, okay, I know that you provide this function. I can just ask you, provide you the data, and you will give me the results, right? And through this NIC, we have a 400 gigabit data flow that either goes to the GPU and to the CPU, and while it moves through the NIC, we can actually apply operations that we define, right? Good. So we said, explain this. So basically, I think this is interesting because now we can put those accelerators we went through on a spectrum. So going from ease of development to maximum performance, right? So the ARM subsystem, as I was saying, is kind of an endpoint on the NIC. So it's like you use your normal computer, basically, right? But closer to the network. Then you want more performance, let's say, or kind of more a finer granularity of the applications of the programmability that you want to apply, and you move to the DPA, right, which is optimized for IO intensive, RDMA, and so on, right? If you want to go to the extreme, so you need to be a bit crazy, then you can go to the programmable pipeline and then really have access to the packet flow and play with directly network packets, right? So, I mean, it's a spectrum. You have ease of development and maximum performance, and it's not like an exclusive choice. It's not like, okay, I have this use case, I have to choose where to go. You can, for example, deploy your like coarse grain task on the ARM and then decide, okay, well, this critical part of my application, of my code, goes to the data path or even to the programmable pipeline, right? So it's composable and you can exploit even the hardware accelerators we were talking about. So now the question is, how do we program those devices, right? And Docker is kind of our answer, right? So you can think to Docker as CUDA for GPUs, and now we have Docker for network for smart NICs for DPUs, right? So we have one layer on top layers. We have the applications that are using Docker, and then we have three main components: the libraries. This is what we kind of expect main of applications to use. You can see here the DPA, so to program the DPA or storage or a communication channel. Communication channel is just to establish a channel between the host and one of the devices on one of the programmable accelerators on the smart NIC. Those libraries, but even the applications, if they want to do more kind of advanced stuff, they can use directly the Docker drivers, right? And we will see an example here for FlexIO for directly programming the DPA and RDMA as well, so you can have direct access to to RDMA through Docker. Good question so far. So if you have questions or want me to clarify something, just please interrupt me. So now the next step is to go a bit more into the DPA, the data path accelerator. So as I was saying, this is not classical architecture, right? So this is event-based in the sense that you specify some code from the application, you specify some code and say, okay, I want to execute this code on the device, on the DPA, whenever some event happens, right? And now we have to define what an event is. But basically, we have the application here that says, okay, this is my handler. We call it event handler, right? And then uses the Docker libraries and drivers. Now, you can use either Docker DPA or FlexIO, depending on your needs, to actually offload this code to the DPA, right? And at this point, we have two types of events that you can have. Either RPC, remote procedure calls directly from the host to say, oh, look, I want to execute this function, right, on the DPA, or network events. If you are a bit confident with RDMA, you know that we have this completion event. So whenever an operation completes on the receiver side, on the target side, a completion event is generated by the NIC, right? And now we can attach an event handler that we specified on the host to this completion event. So say every time you see a completion event, please trigger a thread running that code I specified on the DPA, right? And then on the DPA, you can have, again, device-side libraries to actually communicate with the rest of the world. You can use Docker DPA device-side or FlexIO device-side, and everything then interfaces a real-time operating system over there. So if we look a bit at the architecture, we have 16 cores, RISC-V cores, and each core is composed by 16 threads. So this is hardware thread contexts, each one with its own L1 and shared L1 code. And then they all share a high bandwidth L2 cache. And this is a particularity. I was saying you, this is not classical architecture because there is no actually DRAM here. So this is all caches, as you can see. So if there is a cache miss, this will actually go to either the DPU memory, or the ARM subsystem memory, or directly to the host memory via PCIe, right? So we have all kind of components here. For example, to open a window over either GPU or host memory or DPU memory and access the memory directly via load stores. Now you have to understand that this is not memory that is on the NIC, right? It's through PCIe. So normally, how do you access it, right? It could be challenging to just do a DMA to access like 8 bytes. Instead, with this mechanism, you can just do load stores, and they will be automatically translated to a PCI transaction in order to go to the target memory. So what is the flow? Yep. So this caches is 1 megabyte today, L2, and 1 kilobyte per core, right? In the next generation, they are probably going to be bigger. But the point is, like, it's what you have to, you don't want to run a full application on the DPA. It doesn't make sense, right? You want to run some precise tasks, and then those sizes are actually enough. Good. So what is a bit the flow? So what do you have to do to program the DPA? First of all, you write the code on the application side. So it's like CUDA, right? You write your kernels. Now they are event handlers. Okay. You compile the code, and I have an image for that. Then download the code to the DPA, and then specify which are the events that you want to trigger the code you're downloading. So this, I think, for some of you is kind of familiar. So you have the kernel, so the event handler, even in the figure is actually called kernel, and the Docker DPA device library, right? Now we don't have CUDA-CC, but we have DPA-CC, right? That just produces the executable for the DPA. Right? You don't want to run this on the host. Then you take this with the DPA program, the host application code that runs on the application, and the device and the host side library, and compile everything with your normal compiler in order to get an host executable, right? That will contain stubs for the DPA that then will offload through the host side libraries. It's all transparent, right? So just to give you a quick overview how to actually program this. So you, you have to care about three things normally, or two things, like memory management and how you execute the code, right? So for memory management, actually, I think I'm going to skip, not too interesting. You have the usual stuff, stack memory, heap memory, and this external registered memory that is what I was telling you before, that you can access via load stores, even GPU memory, for example, from the NIC. And just to show you the two things, the two kind of triggers that you can have, either RPC. So in this case, you specify the device code. This is single C file, right? You specify the device code. In this case, we are just saying, okay, wait for some flag. If this flag arrives, return, nothing really special. And this is the host code where you create the device and run the function directly, right? So this is RPC. You say, okay, at this moment, I want to run this function. Think about this for, I don't know, if you want to initialize some state on the device. On the other side, and this is more interesting, this is the network events. You want to specify an event handler that you don't call like specifically from the host, but you want it to be triggered, right? So again, same DPA function. This is nothing special. You get a completion, so this completion event, get the data from this completion, do some work, and then arm again the completion just to say, okay, whenever a new event comes, call me again, right? And the host code, you create process, you create the event handler, uh, create the completion queue for the RDMA, and then say, okay, from this moment on, if something happens on this completion queue, then trigger this event handler. So, I mean, nothing really super complicated, but still, I mean, I think the simplicity that it has, it allows you even to just go and experiment with it and try to offload your own code. So as a example here, we have two initiators. So we want to count packets. So we have two nodes that are sending packets, and we just want to count and stop when they go to 4. Right? How do we do that? Now you can have two RDMA connections. So these guys are doing sends, right? And you are doing receives. So actually, first thing you have to do is post the receive, right? So, and how you post the receive is through an RPC, right? So you do RPC, you call the RPC function that just posts the receive, so you are ready. And then this guy starts sending, and the completion now goes to triggers a DPA thread. So what I want to show here, and the DPA thread just counts, and if it reaches 4, in this case, to each, then says, oh, I completed, right? In this case, actually, it notifies another thread, but this is not super important. What I wanted to highlight here is that this code is what you will normally have to execute, right? Like thread pooling, like, okay, I'm receiving something and then I need to trigger the thread, right? If you want to write this on an x86, you have to manage all this execution, this triggering, these resources. This is all done in hardware. You don't have to care about it. You just write, okay, this is the function I want to execute. Please just wake me up when it's time, right? And this is hardware, so it's for sure faster than what you will do in your software library. Good. So this kind of concludes the DPA part. So do you guys have questions?
I have a question from the software architecture point of view, especially from the programmer point of view. So now that we have all this intelligence in the infrastructure, let's say, or let's say the local infrastructure, from the point of view of writing software, do we have already a trend on having something like a single source way of distributing this knowledge? So if I have my application and I want to do a node reduce, I know what is the bit I want to put into that area of the network capability and the network compute capability. Now, do I need to write custom code and then deploy up front? So I need to know that that specific switch has NIC has that capability, or can I do everything from my software point of view in one place and then everything is going to be distributed when is the compile/runtime?
Good question. So I would say this goes back to the first slide, right? So the level of flexibility and programmability you want to exploit. So there are communication libraries that do this for you. Like they can understand, okay, you're doing a node reduce. What do I have there? Like, for example, if you have a collective operation framework, and you don't want to write a collective operation, right? It's kind of the same thing. You want to just use a library that knows how to implement that collective operation, right? And now the idea that now, as we have this programmable engine, that collective library will understand, okay, is there a programmable engine on this system? Can I use it? For example, can I offload all the progressing part of the collective to the ARM subsystem or to the DPA in order to just like free CPU cycles and be more energy efficient? Or if from the application perspective, you say, okay, actually, I know what to do better than the application because maybe you are dealing with a very custom use case, right? That you want to flip some bits in the collective as they go, is not a standard operator of the already used, whatever, then you can do your own stuff, right? And then, I mean, I think this is an interesting question, like if those like collective libraries should open you to actually insert your own code as the collective goes. So take care of all the rest and just allow you to customize it a bit. Or just as today, okay, if you want to use that by yourself, then yeah, write your collective, right? Yeah.
Salvo, I have a question for you, also for Gil, probably. So far, CUDA was a success in terms of programming model for GPUs. So how do you envision the future? Because in this case, you are introducing basically concepts that require probably a new programming model to integrate network capability as well as GPU programming capabilities. Something like Pegas models with some extensions or something else. What is will be the future here?
Yeah, there are two parts to try and answer that. So I think that, you know, Docker is going to be the platform that will allow you to do whatever you want to do with network, and CUDA is all the compute. Now, the combination, we will do all kinds of programming models. You probably know that even today we have, you know, on top of CUDA, we have NVSHMEM, which is a Pegas programming model, but we also have Nickel that allows you to do massive pathing programming. We don't really choose that. We will give you multiple options always because, you know, graph problems requires different characteristics than fluid dynamics. And I don't think there is one programming model that will win. Unfortunately, you will have to choose the right way to do that yourselves, and we will provide the infrastructure. I think that, you know, I've been with NVIDIA just for a few years. I came from Mellanox, we've been a networking company. And I did have the opportunity to see the way NVIDIA are working. And I think the most interesting part is that we spend tons of resources on providing you the right SDKs, not solving the problem for you, but giving you the SDKs from, you know, CUDA SDKs like cuDNN and cuGlass and whatever, there are tens or hundreds. We will have the same for networking and offloading and acceleration, for security, and for everything that we believe, you know, has the opportunity to ease your pain of solving the problem. You will also have to choose the right ones.
And to add to this, I think like this is in the early stage of its life, right? This new programming models, this new way of offloading things. So like while we can propose SDKs or like a vision how to use it, I think we expect also the community actually then to experiment and provide feedback. Okay, I want to like use floating point operations on the DPA because this use case is a killer use case. So what to do?
The answer is fair enough, but I'm provocative. So I'm not satisfied. So far, one part of the team was okay, develop the direction towards Docker, another part of NVIDIA pushing on the programming side, programming model side. So now in the short term, it's okay providing an SDK and you decide what is the best for the application that you have. Fair enough. But we are convergent on many different things on AI, also on programmability. With JAX, for example, now you inject CUDA code at in the backend directly. So, and I think the next step will be redesign this layer in order to converge a network and a content part. I'm not saying that it's going to happen in 2 years or tomorrow, especially if you have Salvo.
And you are recording it, right?
But this is something that we have probably as a academic to look into. Probably Daniele, we should look at, and I don't know if this is something that is not in the roadmap, but is reasonable enough to look.
So I think that, convergence, we have our own beliefs. I don't think we should decide where it should converge. I think the users should, right? And they will eventually. I don't know if it's fortunately or unfortunately, today there is one application that rules the world and everyone goes there, and the rest is somewhat losing attention. Unfortunately, it seems that at least for the coming years, whatever fits this application will be the de facto standard. Going back to that programmability, I just want to give one interesting example, right? So even for the DPU, you want something to run on your DPU, right? And offload or accelerate or give you some service for your application in the network. Even us, we have multiple options how to do that, right? Today, we drive two ways. One is the Docker way, but I'm working with a research team on a way to just do that with OpenMP, right? So you use Pragma, and I want that code to run, and I don't want to know how it happens. We work on both. And the one that will choose which one is better is not going to be me, hopefully. Yeah.
Or Salvo, which is the follow-up, basically. Do you think that one of your best papers was on spin? It's something that can fill this gap, actually. So a programming model that allows to packet processing as well as part or integrates that.
So actually, I think that like the DPA as it is today goes very much in the same direction of spin. So I don't think that like spin will revolutionize what we have here. Yes, yes, totally.
So, Flavio, you stole my question, so I blame you partially. And I think now I understand a bit more by your answer. So, the idea is basically OpenMP task pooling, right? So you create a pool of tasks, and you say one task do that prior to not really parallel in some sense, but like you're defining the particular thread to do some task and you don't care in the job. But then at some point, host should shrink, right? So because it's still host centric, not like just if you think about computing. So
Right. Yeah.
how do you? So
Good point.
what I want to understand how much you rely, as you're saying, you user side, you don't have to, you just rely on the DPU capability, or how much we as a user to make sure that extension to be the correctness of the output that you more or less that you try to do.
Yes. So if I understand your question, like the thing is that if you run, there is a big difference here, because if you run like OpenMP, as you say, is kind of host centric, right? So you decide, okay, I have this task, I want to launch a bunch of threads to run it. If you do this on the network, it's not, you don't decide it. It's the network that decides for you, right? Because it depends on how the data arrives, on when the data arrives. So even like understanding which form of parallelism is not like super clear from the beginning. Like you have to take in consideration other aspects like the arrival patterns, how much parallelism you can exploit. If there are dependencies, you get the first message, okay, can I start processing the second message before? So you want a pipeline or you want to go data parallel. So all this kind of stuff, I think, needs to be explored and depends on the specific use case. Good question. Yeah, I think they are orthogonal and they are meant to be used together. This is my personal opinion.
So my question is similar to Flavio's, but on the profiling side. So how much support do you have from developer tools like Insight Compute, Insight Systems for the Docker drivers? So do they recognize them and then show there's an event or kernel launch, etc.?
Yes. So so for debugging, you actually can attach GDB today to the DPA from the host and just debug your application. For profiling, it's a bit challenging because if you now instrument your application on the DPA, which is RISC-V, so if you now spend cycle for profiling, you are actually changing everything. While if you do this on an x86, it's okay, right? I mean, you don't influence a lot. Um, so we have two basically approaches. One is external profiling. So the hardware gets for you counters that exposes to the host, right? So you don't touch the DPA code, or you can have the usual ones like to get the time, the cycles, the instructions, and all this kind of stuff directly on the DPA. So if you want to measure specific sections of code.
Sorry, one that is specifically on that. I just want to add, we work very closely with the Insight team, and what you have today is what you have today. Definitely tomorrow you will have more. I cannot say that it's perfect today, but I can say that we realize the need for much better, integration of the networking part and the compute part, specifically for Insight and that kind of.
Okay, so maybe can I get 15 minutes more just to quickly?
You asked for a question.
True, and I'm regretting it.
The story of our idea.
So I had the bad luck of knowing Flavia. Good, good.
Yeah.
Okay, so I just want to go quickly through this use case where to show you now how we use both in-network features and DPA in this case to accelerate collective operations, right? So to actually motivate this a bit, I have to make a step back and I have to like zoom out quite a while. So we go back to FSDP. Now, I mean, fully sharded data parallel. Gil talked about data parallel, like what happens if the data doesn't fit, when you're training AI, if the data doesn't fit on a single GPU. And FSDP is actually asking also the question, okay, what if also the model itself doesn't fit, right? This is called model parallelism. There are multiple ways to actually do model parallelism. FSDP, fully sharded data parallelism, is one of them. So I don't want you to, if you don't know it, I don't want you to understand or to explain the details now. They are not important. I just want to get you to the problem that we have there and how we solve it, right? So the idea is, okay, we have our model, and this doesn't fit on a single GPU. So what we do is we partition it in FSDP units, right? And the idea is to train these FSDP units, or not one at a time, but to keep one unit on the single GPU at any time, right? So you don't have to keep the whole thing, just a single unit. So this is the memory requirement that you have on the GPU, right? And then, so this is the first type of splitting that you do. And then inside an FSDP unit, this is the sharding. You have your parameters here. You put everything on a flat buffer, and then you kind of partition on the GPUs, right? So these boxes 0, 1 until 15 are GPUs. This is, you can imagine this as a compute node that you have seen in the video Gil presented, right? And but then you realize that, okay, I mean, if we partition, it's not enough then to just go every GPU goes by itself and tries to train. Then you need to synchronize somehow. And the kind of synchronization you do, you have the forward pass and the backward pass. So like inside an FSDP unit, in this example, we have just 4 parameters, right? So those are partitioned among the different GPUs, like in this way. So they are sharded. So nodes here, you can imagine them as GPUs. And then when doing the forward pass, you have to aggregate again, not to aggregate, but to gather those parameters. So you need to do an all gather operation. Like here is a simple scheme. So these are the nodes. Everybody has a small chunk of it, and you want to actually have all nodes have all chunks, right? So you basically you end into this situation. When you are in this situation, you can actually do the forward pass. So now you see the requirements. It's just an FSDP unit, right? And then you can free it and move to the next one. So just focus on the all gather here per FSDP unit. When you do the backward pass, you have to do something similar in the sense that you have to gather again, do an all gather to get all the weights, right? Then you compute the loss and get the gradient. But now these gradients, you can see they are different because there is the data parallelism part. Each GPU will actually run on its own micro batches, mini batches, sorry. So it will, the backward pass will result in different gradients, but now you remember that actually not all GPUs need to know all the gradients, need to update all the weights because it's sharded, right? So you don't need a non-reduce like before, you actually here need a reduce scatter. Reduce scatter is, okay, all nodes have some partial results and you want to aggregate them, but not distribute them like fully, like you want that the first row, for example, goes to the first node and so on, right? So in this way, you can see you get the updated, the full gradient, right? And since the node 1 has the weight 1, let me go one step 4, you can see it here, right? So it just needs that gradient to actually update the weight and then move to the next iteration. So what we end up with is this kind of pipeline. So you have the all gather for the forward pass of the first unit, you complete the all gather, and then you can start the forward pass. And then while this is going, you do the all gather for the FSDP unit number 1, because those are independent, right? So you can just overlap and so on, right? So, but you can see that at some point you start doing all gather for the forward pass of the FSDP unit 2, and you start the backward. And now we are getting to the problem. The all gather, this is for the backward. You see here, you complete the all gather and do the backward. And then you do the reduce scatter. There is a dependency here, right? So all gather, backward, and reduce scatter, right? And in the meantime, you would like to start the backward of the other FSDP unit, number 1, right? So actually, there is no reason why these two are serialized. Like, since those are independent, there is no data dependency here. They can be just overlooked, right? But in practice, they cannot. And I'll explain why. If we don't use our solution, right? so just to explain why I need to run this short, I also have a video, but it's short. It's not. So this is the ring all gather. So how it is normally implemented with a ring. This is very similar to what Gil was showing before, actually. So everybody has its own chunk, and then you have everybody communicates with just the next. So this is CPU, but you can see them as GPUs, right? So they send the chunk to the next one and receive a chunk from the previous one, and in the next iteration, they again send the chunk they just received to the next one. So they keep forwarding the chunks that they receive, right? Until everybody knows all the chunks. Okay, so now just focus on one CPU. Can you say how much data we are sending over the network? Like this buffer is N, how much data we are sending? So actually, how much data we will need to send? Like look at this scheme here. So you need to propagate the data to all nodes. N, correct. You send the whole buffer, right? Great. And so this is what we answered. And how much data we are receiving? N as well, right? Perfect. Now during the reduce scatter, right? So assuming we use sharp, we'll explain it for the all reduce, it worked for reduce scatter as well, right? So yes, it's here. So the reduced scatter, you anyway have to send, even if you have just partial results, so n partial results, you have to send them all out, right? It's optimal, like asymptotically, because I mean, you cannot do better than sending out your partial results, right? You have to send them at least once over the network, and so it's O of n, again here, and you're receiving just the reduced chunk. So it's O of 1. You are just receiving from the network one chunk, the one you own, because this is the reduced scatter. If it will be O reduced, it will be O of n again, right? O reduced wants to propagate to everybody. Now, what I want to focus on is, remember, the all gather and the reduced scatter could run in parallel. But now you see that we are sending O of n here and O of n here, right? Now, what happens if two of us want to pass through that door all together, right? Probably if you go with me, we cannot pass together. We have to serialize, right? So, because this is the bandwidth of that port, right? Okay, so if we want to send 2 times the data, the bandwidth doesn't grow, it's fixed, we will take twice the time. So this is why they cannot be overlapped. You can try to overlap, but anyway, it will take the same time, right? So what we propose is a scheme that uses the multicast primitive that actually sends in O of 1, sends just O of 1 data and receives O of n. And now you can see that when you match this with sharp, you have O of n on the sending side plus O of 1, so it's okay. And on the receiver side, you have the same balance, right? So how do we get there? We use the multicast primitive, and the idea is kind of similar to sharp, but without aggregation. This is just distribution. So we have the nodes and the switch here in this example. So like A now just sends packets, right? And the switch duplicates them. So you don't have to send to A, to B, and C. You just send it once, and the switch will duplicate the packets for you. So now we are doing an all gather. So B wants to do the same, right? And C wants to do the same. And these animations are too long. And this happens all at the same time, right? So this is why we need O of 1 in sending. We just send one, and this way the network will actually replicate the packets for us, right? So this is the basic idea how we get to, we not use the ring, because the ring has also the problem of the latency issue when scaling out, right? So this doesn't have it. Good. So what are the issues here? So if we look at today's multicast primitive, it supports only single MQ. So you cannot send a 1 gigabyte message. And if we look at AI, actually the messages range from 10 to 100 megabytes, right? So like that, the sender will need to actually chunk a lot. Does not support one-sided semantic. So you cannot write to the receive buffer directly. You have to stage the data somewhere and then copy it, right? So now imagine if you are getting 10 megabytes of data, you have to fully receive those 10 megabytes and then copy it. So it's not great and it's not reliable. Even if it's with low probability, it can still happen that some messages are dropped, right? So you need to have some recovery protocol. So the idea is, okay, can we use now the DPA, right, to implement an abstraction, a new primitive that offers a large message, one-sided and reliable multicast. So this is a bit, I think, also the spirit of this accelerator. So can we build new abstractions or new primitives that are not available in the hardware we have today, right, and offer them to the applications? So now the application doesn't have to care, okay, my multicast is actually single message. It's not reliable and doesn't have one-sided. It's just hidden. There is no hardware, but it's kind of software implemented into the NIC directory, right? So this is what we do. Just a quick scheme here. So we have the NIC, the DPA, we have the staging buffer, because remember, we have to stage buffer for the way the multicast is today. And this is the host side where we have the receive buffer. So as we get packets, the multicast packets, we just copy them to this is the NIC that we don't do this on the DPA. We don't, usually you don't want to touch a lot of data on the DPA because it's expensive, right? So the NIC, we just receive the data and get it into a stage buffer, but then it will generate a completion. And if you remember, the completion triggers a DPA thread, right? And now we can say, okay, look, now we received this chunk. So what do we do? First of all, we copy the chunk from the staging buffer to the receive buffer. We actually implement reliability. So using a bitmap just to understand like if something is missing at some point and when we received all the chunks. So when we see all ones here, this means that we received everything, right? And once we realize that, we just signal the application. So the application is totally unaware of all this stuff is happening here, right? We signal the application, okay, the all gather completed. Take it. Yeah.
Probably not. Maybe I didn't understand completely, but all of this is true if we only have one switch. But if we want to do this over two, how do we handle also with the fact that the multicast does not guarantee ordering eventually?
Good point. Yes. And this is so the idea is that in the multicast you can do like you can specify an immediate value that tells you the position of that chunk in the received buffer, like the offset, right? So you now see that we are using this staging buffer here, right? So we stage it. We don't care where we stage it. We just care that the final position has to be the correct one. So we use this information that we get in the completion notification, right? That say, okay, actually, this is the offset I want this data. And this data copy, this is what that we start from the DPA, we copy it to the right location, right? And you remember this thing that I was saying before, okay, if you get 10 megabytes, then you have to stage 10 megabytes and then copy 10 megabytes receive buffer. But if you see here, we are pipelining on a 4 kilobyte granularity, right? So we are kind of hiding that copy cost, right? So we pay the additional cost of copying 4 kilobytes. It's okay over 10 megabytes. Okay, great. Yes, yes, I finished. I'll skip this and just jump to the conclusion so we can go to the break. So, oh, this is what I wanted to show actually. So the question is, okay, can the DPA actually sustain that? Because it's all matter of bandwidth in the end. So can we do it, right? And this is the throughput that we can sustain on the DPA as function of the number of DPA threads that we use to implement this scheme. And you can see that using 8 DPA threads over 256, right, we can actually get to line rate, in this case was 200G, this setup, right? You see, I don't have the time to explain, but basically you see is a new type of multicast that today doesn't exist that actually allows you to avoid the staging. So you just need to handle reliability and completion on the DPA, right? So it saturates faster. And this is actually what you will get if you will just use one CPU thread to do the same scheme, right? And now the question you can say, okay, Gil was saying that we are going to crazy speeds, to crazy data center. How does this scale? Like 200G is the past, right? So what we did is kind of an estimation. And we don't have 1.2 terabits network cards yet, so we cannot really test. So, but if you consider the message rate, basically, this is what you care, how many packets you can process per second on the DPA, and then you multiply this by the size, you start getting what could be the bandwidth. So it's kind of an estimation, but this is what is interesting here is number of DPA threads, and again, the two schemes. So with 64 DPA threads, again, over 256, and for this generation, so assuming that the network goes to 1.2 terabit, and the DPA is what we have today in Connectec 7, with 64, we are actually able to go to 1.6 gigabit per second. Right, so apparently it could scale well. Okay, so this kind of concludes my presentation. So we went through the BlueField-3 architecture and the importance of speed and flexibility, in particular programmability, made a deep dive on the DPA, which is just one of the accelerators we have there, and went through a use case where we used the in-network features like the multicast and in-device features like the DPA to actually accelerate and hide the complexity, expose a new multicast primitive basically to the application. And that would be it.